Hey guys, how's it going? Mr. Mitchell here. In this video we're going to look at factors affecting charging and discharging time for capacitors. So let's get started. Now it starts here by saying that the time taken for a capacitor to charge or discharge depends on the capacitance of the capacitor and the resistance of the resistor connected in series with it. If we look at capacitance first, it says here that increasing the capacitance increases the charging and discharging time because more charge is stored on the capacitor. So a good analogy to think about is filling up a bucket of water where the water represents your electrons or your charge and the bucket itself represents the capacitance of the capacitor. So let's say you were to fill up a bigger bucket with water, that is like using a capacitor of larger capacitance. And obviously that larger bucket is going to take a longer time to actually fill up with the water or fill up with the charge. So here's two graphs for the charging capacitor case, where we've got potential difference against time and current against time. So remember, for the charging capacitor case, potential difference will increase over time and current will decrease over time. But let's say we have a small capacitance for the capacitor to begin with, then notice how its potential difference is going to reach its maximum value in a shorter time. Whereas if we use a larger capacitance, it's going to take a longer time to reach its maximum potential difference. Same for the current. If it's a small capacitance for the capacitor, then it will take a shorter time to decrease to zero. However, if it's a larger capacitance for the capacitor, it will take a longer time to decrease to zero. We can also see the same for the discharging case of a capacitor. So remember, potential difference will decrease over time and the current will decrease over time from a maximum negative value. So if we have a smaller capacitance for the potential difference against time graph, it will take a shorter time for the potential difference to decrease to zero and a longer time if it's got a larger capacitance. And for the current against time, you can see it's going to take again a shorter time to decrease to zero for the current, but then a longer time for the current to decrease to zero if it's using a larger capacitance capacitor. So we've just seen how increasing the capacitance of a capacitor will increase the time for charging and discharging, but we also have the same happening for resistance. So increasing the resistance of our resistor in our circuit increases the charging and discharging time because less current flows at the start of the process. So going back to our analogy of the bucket and the water, if you think about the resistance of a resistor in a circuit as being the tap, then if you increase the resistance of the tap, you essentially are closing the tap, which means that less water will come out of that tap, i.e. less current will flow. So increasing the resistance in the circuit will therefore take a longer time for the capacitor to charge and discharge. So here's a couple of graphs just like we saw for the capacitance case earlier. So for the charging case, first of all, we've got potential difference against time and current against time, and you can see that for a small resistance of the resistor, the potential difference takes a shorter time to reach a maximum value, whereas using a larger resistor it takes a longer time. And for the current decreasing to zero over time, if you're using a small resistance resistor, then it's going to decrease to zero in a shorter time, whereas if you use a larger resistance resistor, it's going to take a longer time to decrease to zero. Notice also on this graph how the current starts at a smaller maximum value on the graph for a larger resistance resistor, and that's because if you think about Ohm's law, V equals IR, remember the maximum current Imax will be equal to the supply voltage Vs divided by the resistance R. So if you use a larger resistance resistor, then you're increasing the R value on the denominator, which means your Imax value would be smaller. And also for the discharging case, we have potential difference decreasing over time and current decreasing from a maximum negative value to zero over time. And you'll see the same thing happens for a smaller resistance resistor. The potential difference takes a longer time to reach zero, and a larger resistance resistor takes a longer time. Whereas for the current against time, we have our small resistance resistor taking a shorter time to decrease to zero, and our larger resistance resistor taking a longer time to decrease to zero as well. And again, just like before, we have a smaller maximum value of the current, although the only difference here is that this time it's negative. Lastly, it says to note that the supply voltage in the RC circuit is also a factor. So increasing the supply voltage increases the time for charging and discharging, since it will take the capacitor longer to reach a higher voltage. So let's say you were using a 3-volt battery to begin with. If you then replace that with a 6-volt battery, your capacitor would take longer to charge and discharge in the circuit because it's going to take longer to reach that maximum voltage across it. Just to show you a quick simulation to help you understand these factors. So let's say we start off with the charging case, and if I have a 33 microfarad capacitor and a 150 kilo ohm resistor, if I click play here, you'll see that we get the potential difference increasing over time, and we also get the current decreasing over time. However, if I now swap out the capacitor and resistor for ones of higher values, so let's say we choose the 56 microfarad capacitor and the 220 kilo ohm resistor this time, so both the capacitance and the resistance have been increased. So if I click play here, you'll notice that just like before, we have the potential difference increasing over time and the current decreasing over time. However, the potential difference is taking longer to reach its maximum value here, and the current is also taking longer to decrease to zero. It's also the case that the current is starting at a smaller maximum value here than before. So to summarise all the results, the gold or orangey curves here are the first set of curves that we saw, whereas the purple curves are the second set that we saw. So you can see there that using the capacitor of higher capacitance and resistor of higher resistance, we have a longer time to reach maximum voltage, and we also have a longer time to reach zero current, and it starts at a smaller maximum value of current. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.